Hello everyone. Today we are going to analyze this beam using slope deflection method. Before analyzing, let us see the beam one time. In this beam, there are three spans: span AB, span BC, and span CD. Also, there is a overhanging span DE. In the span AB, there is a point load 40 kN acting in the center. In the span BC, there is a concentrated moment 80 kN meter. It is acting in the clockwise direction. In the span CD, there is uniformly distributed load 48 kN per meter acting for the full span. In the overhanging span DE, there is a point load 40 kN acting in the point E. The moment of inertia for the span AB is 3I. The moment of inertia for the span BC is 2I. For the span CD, it is 2I, and for the overhanging part, it is I. AB and BC are 4 meter long. CD is 5 meter long. The overhanging part is 3 meter long. In this beam, there are 7 moments we have to find. In the point A, there is a fixed support. In the fixed support, there will be a moment. Here, the moment is MAB. In the joints, there will be 2 moments. In the joint B, there are 2 moments, MBA and MBC. In the joint C, there are 2 moments, MCB and MCD. And in the joint D also, there are 2 moments, MDC and MDE. So totally we have to find 7 moments. Also, we have to find 4 vertical reactions, RA, RB, RC and RD. In the joint D, we can easily find the final moments because on the right of D, there is overhanging. To calculate MDE, we have to multiply the point load 40 kN with the overhanging distance 3. When we do that, we are getting 120. MDE is acting in the anti-clockwise direction, so it should be negative. In this case, we have to apply a negative sign with the load so that we will get a negative moment. The values of MDC and MDE will be same, but they will have the different signs. MDE is acting in the anti-clockwise direction. It should be negative. MDC is acting in the clockwise direction, so it should be positive, but both of them will be having the same value. In this concept, we can calculate MDC very easily. For that, we have to just change the sign of MDE. When we do that, we are getting positive 120. In the slope deflection method, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. In the roller support also, there will be slope. In this beam, in the points B, C, and D, there are hinged supports. So, the number of supports in which slope can occur is 3. In the point B, there is theta B. In the point C, there is theta C. And in the point D, there is theta D. So, in this analysis, there are 3 unknowns. To find out these 3 unknowns, we need 3 equilibrium equations. Now let us see how to make these 3 equilibrium equations. In the joint D, we have calculated MDC. This is our first equilibrium equation. In the joints, the summation of the moments will be 0. In the joint B, there are two moments, MBA and MBC. When we add these two moments, it will be 0. In the joint C also, there are two movements, MCB and MCD. When we add these two movements, it will be 0. It is our second equilibrium equation, and this is our third equilibrium equation. Now let us calculate the fixed end moments. First, let us find them in the span AB. In the span AB, there is a point load 40 kN acting in the center. The formulas for the fixed end moments are minus WL upon 8 and positive WL upon 8. Using the formulas, we are getting M of AB and M of BA. Now let us take the span BC and find out the fixed end moments. In the span BC, there is a concentrated movement 80 kN meter acting in the clockwise direction. This movement is acting in the center. The formulas for the fixed end moments are positive m upon 4 and positive m upon 4. Using the formulas, we are getting m of BC and m of CB. Now let us make the fixed end moments in the span CD. In the span CD, there is UDL 48 kN per meter and it is acting for the full span. The formulas for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. Using the formulas, we are getting M of CD and M of DC. We have calculated the fixed end moments in the spans AB, BC and CD. No need to make the fixed end moments in the overhanging span. Now let us make the slope deflection equations. First, let us make them in the span AB. Let us apply the fixed end moments in the equations. The moment of inertia for AB is 3I. So instead of I, we have to apply 3I in both of the equations. Length of AB is 4. Let us apply that. In the fixed supports, there will be no slope. In the point A, there is a fixed support. So theta A will be 0. Finally, in the span AB, we are making two equations. Now let us make the slope deflection equations in the span BC. First, let us apply the fixed end moments. The moment of inertia for BC is 2I. So instead of I, we have to apply 2I. Length of BC is 4. Let us apply that. Finally, in the span BC, we are making two equations. Now let us make the slope deflection equations in the span CD. First, let us apply the fixed end moments. The moment of inertia for CD is 2I. So instead of I, we have to apply 2I. Length of CD is 5. Let us apply that. In this equation, let us make the first equilibrium equation. We have already calculated MDC. Let us apply the value of MDC. Then let us take this 100 on the left side. It will come as negative. 120 minus 100, we will get 20. This is our first equilibrium equation. We have made one equilibrium equation, but we need three. We know that the second equilibrium equation can be made in the joint B. In the joint B, MBA plus MBC will be 0. We have already made the slope deflection equations for MBA and MBC. Let us add them. 20 plus 20, we will get 40. Then let us take 40 on the left side. It will become negative. This is our second equilibrium equation. Now let us make the third equilibrium equation. In the joint C, MCB plus MCD will be 0. We have already made the slope deflection equations for MCB and MCD. Let us apply them. 20 minus 100, we will get minus 80. Let us take minus 80 on the right side. It will become positive. This is our third equilibrium equation. We have made three equilibrium equations, the sixth one, seventh one, and eighth one. Now let us use calculator and solve these three equations. If you do not know how to solve three equations in the calculator, see the description below. There is a link. You can click the link and watch the video. Finally, we are getting the unknowns. Now let us find the final moments. When we apply the value of A theta B in the equation number 1, we are getting MAB. When we apply the value of A theta B in the equation number 2, we are getting MBA. When we apply the values of A theta B and A theta C in the equation number 3, we are getting MBC. When we apply the values of A theta B and A theta C in the equation number 4, we are getting MCB. When we apply the values of E theta C and E theta D in the equation number 5, we are getting MCD. So in this analysis, we have calculated all of the moments. In this analysis, we have calculated all of the moments. For MAB, we got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we got a negative value. So it is also acting in the anti-clockwise direction. For MBC, we got a positive value. That means it is acting in the clockwise direction. Previously, we assumed that MBA would be acting in the clockwise direction and MBC would be acting in the anti-clockwise direction, but our assumptions are wrong. For MCB, we got a positive value. That means it is acting in the clockwise direction. For MCD, we got a negative value. That means it is acting in the anti-clockwise direction. Now let us find the vertical reactions. First, let us take the span AB and calculate the vertical reactions. In the span AB, there are two moments, MAB, which is acting in the anti-clockwise direction, and MBA, which is also acting in the anti-clockwise direction. First, I am going to find out RA. For that, I am going to take movement about B. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 4 meter, so for RA. The point load 40 kN is acting towards the point B in the anti-clockwise direction, so it will be negative and the distance is 2 meter. Then we have two movements. Both of them are acting in the anti-clockwise direction, so both of them will be negative. Finally, we are getting RA. By applying the rule sigma V is equal to 0, we can find out RB1. Now let us take the span BC and find out the vertical reactions. In the span BC, there are two movements, MPC, which is acting in the clockwise direction, and MCB, which is also acting in the clockwise direction. In this span, first I am going to find out RB2. For that, I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction. So it will be positive and the distance is 4 meter. So for RB2, the concentrated movement is acting in the clockwise direction. So it will be positive. Then we have two end movements, 19.6 and 58.8. Both of them are acting in the clockwise direction. So both of them are positive. Finally, we are getting RB2. For RB2, we will get a negative value. That means our assumption is wrong. We assumed that RB2 is acting upwards, but actually it is acting downwards. Now let us apply the rule sigma v is equal to 0 and find out RC1. Here we have to be very careful. When we apply the value of RB2, we must apply as negative value because it is acting downwards. Finally, we are getting RC1, which is equal to 39.6 kilonewton. Now let us take the spans CD and the overhanging span DE together and find out the vertical reactions. When we take these spans together, no need to consider MDC and MDE because they will get eliminated. Only we have to consider MCD, which is acting in the anticlockwise direction. When we take moment about D, we can find out RC2. Then we can apply the rule sigma V is equal to 0 and find out RD. Now let us add RB1 and RB2 so that we will get RB. For RB, we will get a negative value. That means RB is acting downwards. Then let us add RC1 and RC2. After adding, we are getting RC. Now we are going to draw the shear force diagram. I am going to calculate the shear force values from the point A. In this case, I am moving towards right hand direction. Upwards will be positive and downwards will be negative. You can see the shear force values. Using the values, we can draw the shear force diagram. Now let us draw the free movement diagram. For drawing the free movement diagram, we have to consider every span as a separate simply supported beam and calculate the bending moments. First, let us take the span AB. In the span AB, there is a point load acting in the center. If in the simply supported beam, point load is acting on the center, the formula for calculating the maximum bending moment is WL upon 4. Using the formula, we are getting 40. In the span BC, there is a concentrated moment. The concentrated movement is acting in the center and it is acting in the clockwise direction. The formulas to find out the maximum bending moments are m upon 2 and m upon 2. Here the moment is 80, so 80 by 2 we will get 40. On the right of the moment it will be positive and on the left side it will be negative. Now let us take the span CD. In the span CD, there is UDL 48 kN per meter acting for the full span. The formula to find out the maximum bending moment is WL square upon 8. After applying the values inside the formula, we are getting 150. For the point load and for the point movement, the free movement diagram, will be in the shape of triangles. For the UDL, the free movement diagram will be in the shape of parabola. Now let us make the end movement diagram. In the direction of the movements, we have to make the diagram. If the end movement diagram comes above this line, that will be negative. If it goes below the line, that will be positive. So here and here it is negative, and here it is positive. Now we can combine the free movement diagram and end movement diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.